Good morning, everyone, for today's webinar series on Distinguished Webinar Series in AI and Cybersecurity. Today's speaker is Dr. Amir Abiri Jahromi. Dr. Amir is currently a lecturer at the University of Leeds. He received his Ph.D. degree in Electrical and Computer Engineering from McGill University, Montreal, Quebec, Canada in 2016. He was a Postdoctoral Fellow at the University of Toronto, Ontario, Canada from January 2018 to December 2019. And Research Associate at the University of Toronto in 2020, collaborating with Hydro-Quebec Research Institute. His research interests include power system modeling, cyber-physical security, reliability, economics, and optimization of power systems. Dr. Amir, thank you so much for spending your time this morning with us at UND. I appreciate the time you have devoted for this, and the floor is yours.
Okay, wonderful. Let me first try to share my screen, I guess. Okay, wonderful. Okay, wonderful. Can you see my screen?
Yes, we can. Yes.
Okay. Hello, Prakash and everyone. First of all, I would like to thank you for the nice invitation and thank you so much for the kind introduction. It is a pleasure to be here. So the title of my talk today is Cyber Physical Security Analysis of Digital Substations. So first, let's take a look at agenda. I'm going to talk a little bit about digitalization of substations, security reference architecture of power systems, cybersecurity in classic power systems. Then I will continue with defense in depth, zero trust security concept, and the importance of real-time co-simulators for cybersecurity analysis of substations. Also, I will discuss co-simulation of communication-assisted protection and also the importance of software-defined networking for substations to improve cybersecurity. And at the end, I will discuss machine learning-based anomaly detection system for substations. So first, let's take a look at the substations. So if we look at substation automation, it is moving toward cyber enablement and IT-OT convergence by using LAN-based communication network IEC 61850 protocol instead of hardwired connection. The main reason behind this is to improve reliability, maintenance prediction, and reduce costs. Also, we would like to achieve improved situational awareness, monitoring, protection, and better basically monitoring, protection, and control. And therefore, there is a need for cybersecurity analysis of substations and protective relays. But before getting into the cybersecurity of substations, it is very important to review security reference architecture of power systems that we have. As you can see in this slide, basically, we have different levels in power systems. We have level 0, where sensors and actuators like CTs, PTs, and circuit breakers are located. Then we have level 1, where protection devices and intelligent electronic devices are located. At level 2, we have automation devices like RTUs and PLCs. Then we have wide area network that basically connects the substations to the control centers. And in level 4, we have basically control center with supervisory control and data acquisition system. And finally, in level 5, we have corporate networks. So if we look at classic power systems, we see that there is a complete isolation between operational technology and information technology. We only have information technology in corporate networks, and then we have operational technology in all other 5 levels that we have in the reference architecture of power systems. Another important thing here is that we have different type of communication networks and protocols in power systems. So each level that we check, we will see that we have different type of communication networks basically and protocols. So now we can look at the pillars of cybersecurity. This probably is very familiar to most of you. So confidentiality, integrity, and availability form the 3 pillars of cybersecurity, commonly known as the security triad or CIA. We have confidentiality that ensures that assets are accessed only by authorized parties. Then we have integrity, which means that assets can be modified only by authorized parties or only in authorized ways. We also have availability, which means that assets are accessible to authorized parties at appropriate times. An important topic here is that if we look at information technology, confidentiality has basically the highest priority, and then integrity and availability. But if we look at operational technology, we see that availability has the highest priority, then integrity, and then finally confidentiality. So as we can see, the priority is completely flipped as we move from information technology to operational technology. So by IT, I mean the application of computers to process, transmit, and store data, typically in a business or enterprise environment. While we mention OT, it basically consists of hardware and software systems that monitor and control physical equipment and processes. Now that we discussed pillars of cybersecurity, it is important to look at the security threats that we normally have in OT systems and IT systems. The threats to security include interception, interruption, modification, and fabrication. Again, this might be very familiar to most of you, and it is just to give the basics to the presentation. So in an interruption, a service or data becomes lost, unavailable, or unusable. In a modification, an unauthorized party not only accesses data, but also performs data tampering. In an interception, an unauthorized party has gained access to data. And finally, in a fabrication, an unauthorized party injects fabricated data. We know that there are very well-known security measures in the IT domain to address these security threats, such as encryption, digital signatures, and authentication, but they are not necessarily applicable to OT domain, basically the substation that we are interested in. And the main reason for that is that most of devices that we have in substations are resource constrained, and also because of the cost. Also, they may not have enough memory, or we cannot easily implement encryption, digital signature, or authentication. And another important thing about OT systems is that when they are installed in an environment like substations, they will remain there at least around 20, 30 years at the minimum. So we do not replace them or change them as frequently as the IT systems that we have. Therefore, it would be very difficult to implement most of these security measures basically in them. So let's take a look at security strategies that we basically had previously in classic power systems. There are basically two main security measures that we had in classic power systems. The first one is security by obscurity, and the second one is the perimeter defense. If we look at security by obscurity strategy, it basically assumes that the cyber attacker's knowledge about the system is very limited. If we look at classic power systems, most of the protocols that we had were proprietary type of protocols. Therefore, the knowledge and information about these protocols were very limited. So people and public didn't have access to this type of information, so it would be very difficult to attack the substation. But these days, as we move toward more standardized type of protocols like IC 61850, where all the information about the protocol is available to everyone, then it is much easier to bypass this security by obscurity strategy. For the perimeter defense strategy, also it assumes that the system is secured by controlling and verifying all traffic coming into the boundary of the system. So if we look at the reference architecture that we had for the security of power systems, if we look at, for example, wide area network, we see that the firewalls are at both ends of the wide area network when it goes to the control center or when it reaches the substation. Therefore, the previous assumption was that whenever we are inside the substation or when we are inside the control center, then it would be very difficult to attack the system. But we know that by IT-OT convergence, these assumptions are not valid anymore. So for example, previously we mostly used hard wires to connect different protection devices or automation devices together to the actuators or sensors, so it was very difficult to attack them. But nowadays that we move toward LAN-based IC 61850 and using different Internet of Things or industrial Internet of Things inside the substations, it would be very easy to have remote access to different equipment and assets that we have in substations or control centers. Therefore, just controlling and verifying all the traffic that comes into the system wouldn't be enough. So the question is, what should we do? Basically, the movement towards cyber enablement and IT-OT convergence necessitates a holistic security strategy based on defense in-depth models and layered protective measures. So as we can see here, for each of the things that we have in the substation, asset, application, computer, network, physical layer, and also policies and procedures should be completely changed and move toward defense in-depth. For example, if we look at the network layer, we have to use communication network segmentation in substations. We need to use software-defined networking and different anomaly or intrusion detection systems. Another very important topic or paradigm shift is the concept of zero trust. We are moving toward a cybersecurity philosophy in power systems where we move toward from old adage of trust by verify to never trust, constantly verify. So basically, by moving toward this paradigm shift, now we have to test any type of traffic that we have in the substation or in the control center constantly to make sure that intrusion or an attack hasn't happened to the system, and we cannot just rely based on the trust but verify paradigm that we had previously in substations. With this, now we can move to the cybersecurity analysis of substations. Basically, we can analyze or examine the security of substations from two perspectives. The first one is cyber attack risk assessment and impact analysis. In this case, we are more interested on the impact of the attacks to the system. This can be done from the operations perspective on reliability resilience assessment. So we consider that the cyber attack has happened on the system, and then we check how it would impact the operation of the system or reliability and resilience of the system. Another important aspect is cyber attack detection, mitigation, and prevention, which is the subject of this talk. We basically look at software-defined networking for operational technology or OTSDN, and also intrusion and anomaly detection system for substations to improve cybersecurity for detection, mitigation, and prevention of cyber attacks. If we look at cybersecurity analysis of substations, basically co-simulators are essential for performing cybersecurity analysis of substations. Co-simulation is about integrating two or more simulators to provide an empirical operating depiction of complex multi-domain systems like substations. We need power system simulators, we need communication network simulators, and we need interface between the simulator for data exchange. So power system simulators are used to model the physical part of power systems. Communication network simulator is used to model the cyber layer. And finally, we interface these two simulators for data exchange between the two simulators that we have. We know that there are many different type of simulators for power systems. So to name a few, we can consider EMTPRV, Power Factory, Dixieland Power Factory. We can consider PSCAD, and so on and so forth, which are offline simulators. We also have different type of real-time simulators like Typhoon Hill, OpalRT, RTDS. All of them can be used for different applications or simulation of different aspects of power systems. We also have different communication network simulators. We can consider NS3, Omnet++, or Riverbed Modeler, and then the data that should be exchanged between the two also depends which type of cyber layer we are considering in the system and we model. In this case, or in the scenarios that we tested, based on we use the real-time co-simulator based on OpalRT simulator and HyperSim, which we used HyperSim, which we use to model the physical part of power systems. Then we also had Riverbed Modeler for communication network simulation. And finally, as you can see in the figure that we have here, we interface these two simulators based on network interface cards and communicate by IEC 61800 protocols basically Goose and SV, which are two very important protocols that we have in substations for power systems. The application that we considered and simulated using this real-time simulator was communication-assisted protection. Here you can see the co-simulation of communication-assisted protection using OPAL-RT and Riverbed Modeler. So on the left-hand side, you can see the protective relay, CT and PT, circuit breaker, and how it is connected to the process bus to send the information to IEDs. And then we had a communication network between the two substations, so we can just communicate with the other remote substation. In terms of real-time co-simulation, on the right-hand side, on the top, you can see the implementation of the communication network that is needed for the communication-assisted protection in Riverbed Modeler. So that part has been implemented in Riverbed Modeler. And then at the bottom of the left part, you can see the protection devices on IED and the power system basically that has been completely implemented in the OPAL-RT real-time simulator using HyperSim. So in order to do the cyber attack and analyze that, we first need to have an attack model. We assume that the objective of attacker here is to force the communication-assisted protection to misoperate during a fault. We needed a benchmark test system. As you can see here at the bottom of the slide, we used the IEEE PSRC-D6 benchmark test system, which is developed by a IEEE relaying committee. And as you can see in the system, we have 4 generators, G1 to G4, which are connected to the rest of the grid through 2 transmission lines. And then, as I mentioned, we consider communication-assisted protection for the transmission lines. And the objective of the attackers was basically to delay the communication between the 2 relays at both sides of a transmission line in a way that the time goes beyond the critical fault clearing time, which we call CCT. And if the time goes beyond that time and the fault remains on the transmission line, the synchronous generators that we have will lose synchronism to the rest of the grid, and they will drop out of the system, and it will become a huge disturbance in the system. So in order to implement the attack, we assume that the fault happens at 80% of the transmission line L1. And then we use 2 types of attack: distributed denial of service attack and false data injection attack. So these 2 attacks are implemented in the cyber part and using Riverbed Modeler. At the top of this slide, you can see the implementation of distributed denial of service attack. This is not the only way that we can implement this type of attack. We could simply just disconnect the SITL link that we have in Riverbed Modeler between the 2 switches to implement the OS attack. And then at the bottom of the slide, you can see the implementation of false data injection attack. In order to implement the false data injection attack, what we did was to use Wireshark. Wireshark is open source software, which gives us the ability to monitor the communication packets, save communication packets, or inject it to the switch that we have. So we basically generated the falsified packets that we wanted to inject into the system. And then we save them using Wireshark and then inject it to the switch to implement the false data injection attack in the Riverbed Modeler for our simulations. Here we can see the outcome of these 2 attacks. So on the left-hand side, you can see the case where permissive overreaching transfer trip protection, which is one kind of communication-assisted protection, is implemented without considering cyber attack on the system. In this scenario, as you can see, the fault occurred at 0.2 seconds. And then because there was no attack, the POTT protection works correctly and cleared the fault immediately after its interception. And as you can see, the generator kept its synchronization with the rest of the grid, so it continued to work normal operation, basically. On the right-hand side, we can see the DDoS and FDI attack results. As we can see, again, the fault has happened on 0.2 seconds, but in this scenario, because the communication channel between the two substations has been under attack due to distributed denial of service attack or FDI attack, it couldn't communicate with the remote substation. Therefore, the fault remained on the transmission line for beyond the critical fault clearing time. And because of that, the generator lose synchronism. And because of that, the 4 generating units that we had in this benchmark test system disconnected from the system. And if an attack like this happens in real world, it will become a huge disturbance in power system and can easily become a blackout in the system and force the whole system to go to a blackout. So in order to address these 2 types of attacks, we started to look at the conventional approaches that we have or potential measures that we have, countermeasures that we have in classic power systems. 2 simple countermeasures that already exist in classic power systems include communication channel redundancy and using more advanced protection like directional comparison unblocking protection. Directional comparison unblocking protection is another type of communication assisted protection, but the benefit of this protection is that if the communication channel is lost, it immediately sends a command to trip the circuit breakers and disconnects the transmission line. Therefore, it may help remove the fault immediately and help the system to survive. But there are 2 problems with these 2. Basically, these 2 countermeasures are the measures that has been classically used in power system for communication network failure, not communication network cyber attacks against communication network. So as we can see, again, if someone or an attacker attack both communication channels that we consider here as a redundant communication channel, the same thing will happen. And also, if the attacker used false data injection attack or a supply chain attack, these scenarios are not useful anymore because they are not able to detect attack or address the attack that we have. So we just show the results again. For this case, to consider only DDoS attack on one of the communication channels or when we have DCUB protection. If we only consider DDoS attack on one of the communication channels, or if we consider DDoS when we have DCUB protection, as we can see here, although the communication channel is on outage, the fault has been removed immediately and therefore the system survived. But again, these 2 scenarios are basically similar to the communication channel failure that we normally have in power systems and can be experienced. So it doesn't represent the whole attack scenarios that can be implemented against communication assisted protection. And as I mentioned, therefore, although they address to some extent the DDoS attack on one communication channel, they are still vulnerable to FDI attacks and supply chain attacks. So we need more advanced solutions to address this type of attacks. So another solution that we considered that are basically for cybersecurity is software-defined networking. Software-defined networking is a programmable architecture for communication networks. And in software-defined networking, as we can see in this slide, the packet forwarding functions in network devices are decoupled from the decision-making functions. So basically, as you can see, we have a data plane where the flow tables are implemented in the switches. Then we have the control plane, which can change the flow tables inside the switches. And finally, we have the application plane where it can monitor the traffic. It can, based on the application, decide to send a command to control plane and decide to change the logics or flow tables that we have in the data plane. So it is important also to mention that we have 2 different types of SDN or software-defined networking, one for IT systems and one for the OT systems. In OTSDN, forwarding devices do not react to unknown traffic by sending it to the control plane for decision making. Instead, proactive mode locks down the flow tables such that only pre-engineered traffic can be forwarded. But if we look at ITSDN, whenever an unknown traffic comes to a switch, it immediately forwards the information about this packet to the control plane, and control plane can decide to implement a new flow rule basically for this new packet in the switches, so the packet can be forwarded. But in the OTSDN, as I mentioned, they do not react to the traffic. So we define the flow tables based on pre-engineering and based on the static flow that we know that we have in the substations. Therefore, they will not be changed, and no one can access the switches and change it. So simply after we implement the logics inside the switches, we can remove the control plane. So it would be impossible for anyone to change the logics that we have in the SDN switches and attack the SDN switches. So there are many benefits for using software-defined networking in substations. To give a few of them, it's simpler, less error-prone configuration of network devices through software, cybersecurity by default model, and whitelisting of communication packets is another important aspect of software-defined networking for OT systems. So if you look at previous switches, they are based on blacklisting. And then finally, we have better network visibility and situational awareness because the application plane can easily monitor the traffic that we have in the SDN switches. And if we have a malicious traffic, it is easier to identify it and remove it from the switches. So in order to implement it in the co-simulation environment, you can see here how we have implemented software-defined networking using Riverbed Modeler, and then we connected to the OpalRT as well to have a complete cyber-physical depiction of the substations. As you can see here, we use Postman application or API as the application plane, and it communicates with the control plane of software-defined networking using HTTP protocol. Then we use Open Daylight, which is open source software for customization and automating the switches for the control plane, and it communicates with the SDN switches that we have in Riverbed Modeler to implement the flow tables within each of the switches that we have. In this slide, basically we can see the implementation of false data injection attack against communication assisted protection when we have replaced the layer 2 switches that we had in communication assisted protection with software defined networking switches. As you can see at the bottom of the slide, we can define the source address, destination address, and packet type for each of the packets that go through these switches. And because of that, any malicious traffic that comes to these switches, it will be immediately dropped and it cannot be passed to the next switch. So the false data injection attack cannot be implemented against software-defined networking, as we can see here. Another test that we did using the co-simulation platform was the distributed denial of service. So we tried to inject many packets at the same time to the switches based on software-defined networking to check how much delay they can cause. Again, as I mentioned, because the flow rules are not defined inside the switches, the SDN switches will immediately drop all the malicious traffic that comes to the switch. And as you can see, the delay never goes beyond 1 millisecond. Another important thing that I have to mention here is that we used OTSDN here, and that's the reason why the DDoS attack is not successful. If you use ITSDN, because ITSDN reports any unknown traffic that comes to the switch to the control plane, if you implement the DDoS attack, it is possible that the delay becomes too high and the DDoS attack becomes successful. So again, it is very important that when we work with OT systems, we use the OTSDN and the unknown traffic shouldn't be reported to the control plane because it might cause a vulnerability to the DDoS attacks in the system. Another subject or area that we considered to address the cybersecurity of substations was basically data analytics for cybersecurity analysis of transmission protective relays. There are different methods that we can use to address cybersecurity based on anomaly detection system and intrusion detection systems. We have rule-based anomaly detection systems. Rule-based ADS normally works based on logs of intruders, footprints, and the main problem with these type of anomaly detection system is that they are unable to identify the corrupt contents of packets generated by a malicious agent. These days, we also have another type of anomaly detection systems that they basically monitor all the traffic that exists in the substation. So there is a new device that can capture all the traffic that goes inside the substation. And then if there is a traffic that shouldn't be there, it identifies and generates an alarm so people can easily identify these type of malicious traffic and remove it from the substation. Another approach is using machine learning-based anomaly detection systems. Here we have two types of detection techniques. We have misuse-based detection techniques and we have anomaly-based techniques. The main problem with misuse-based techniques is that they utilize the signatures of known cyber attacks. Therefore, they are unable to detect zero-day attacks. And also, we know that it is difficult to obtain training data for misuse-based detection techniques due to the evolving and clandestine signatures of cyber attacks. So we know that the cyber attackers are become more able as time goes by. They make new types of attacks. So it would be very difficult to have the signatures of all the attacks to train misuse-based detection techniques. So another type is anomaly-based techniques, as I mentioned, which utilizes system behavior to identify anomalies. That's why we focus on this type of anomaly detection system. So again, we started by developing the attack model and defining the objective of the attacker. The objective of attacker here was to perform a coordinated fault stripping attacks on protective relays in order to cause a cascading failure. We assume that the attacker tries to get access to VT, CT, or the merging unit that exists in the substation, and by falsifying the data, tries to force the IED or protective relays inside the intelligent electronic devices to send a command, falsified command to circuit breakers and open them and force the transmission lines to go on outage. And if they succeed to trip more than one transmission line, because normally the power systems are secure to N-1 security, they can easily cause a cascading failure in the system. The attackers can also attack the commands that directly comes from IEDs, but we didn't consider that because the commands from IEDs can be authenticated, basically. But the measurements, because we have high number of measurements, for example, 4,800 SV packets, it would be very difficult to use authentication and encryption for those type of data because it will cause delays beyond acceptable levels that we have. So we consider three scenarios here. The first scenario is executed through the substation process bus. We assume that the attacker access remotely to the process bus and then tries to inject random false data to the process bus to force the IED or protective relays to trip the transmission line. The second and third scenarios are executed through a merging unit by either modifying a tap setting of CTVT or performing the replay attack. In order to address these type of attacks, we consider an anomaly detection system based on deep learning autoencoder. So as we can see here, the encoder basically compresses the input data to a latent space, and then the decoder reconstructs the input data from the latent space, and we try to learn the behavior of data that we have within the substation. So if an anomaly is detected there, we can identify it and flag it as a cyber attack or block those type of measurements. So here we can see the implementation of machine learning-based anomaly detection system in substation. We consider two modes of operation. So this CDS, or cyber attack detection system, at the bottom of the figure is the one that we have developed. It has two modes of operation: cyber attack detection mode and cyber attack detection and mitigation mode. In the cyber attack detection mode, if it identifies anomaly, it only generates an alarm to inform the operators of substation that there is anomaly in the measurements. And if it uses the cyber attack detection and mitigation mode, after detecting the anomaly in the measurements, it immediately send a command to IEDs to block basically the measurements that are malicious, so the IED and the protective relays inside the IED don't trip the transmission line. In order to train the deep learning-based autoencoder, we changed the following parameters. We basically changed the generation level, we changed the fault location, fault time, to generate the representative data for training the autoencoder. As we can see here, we consider a sliding window of 50 millisecond or 240 samples. And then the window basically sweeps the measurements that we have to learn the behavior of the measurements during the fault in a transmission line or in a substation. It is very important to mention that we need a very good replication of the substation so we can generate this type of data. Otherwise, it would not be appropriate. So the most important challenge to develop this type of machine learning-based cyber attack detection system in substations is to have a very good representation of the substation, considering all the noise and all different data that exists in the substation. So that's a very important point that we have to consider. So here we can see the structure of the anomaly detection system that has been developed for transmission protection. As you can see here, it has different layers in the encoder and decoder. I'm not going to the details of that. Basically, we optimized the number of layers and the structure of each of parts that we have here. Then we use the following matrix to measure the performance of anomaly detection system, including precision and recall. Precision is equal to true positive divided by number of true positive plus number of false positive, and recall is equal to number of true positive divided by true positive plus number of false negative. Again, this part should be very familiar for most of you. Here we can see the reconstruction of real fault measurements in the substation. So as we can see, the measurements from the CT and the voltage transformer was reconstructed using the autoencoder beautifully. So there is not major difference between the two, and the error level was very low. And then we tested this anomaly detection system for three types of attack scenarios that I mentioned. So we first used the random data injection into the process bus. As we can see at the bottom of the slide, the autoencoder was not able to reconstruct the random data. So it was easy to identify this type of attack. We had 100% recall and 100% precision. In the second attack scenario, as I mentioned, we changed the instrument tap setting. Again, if we look at the figures at the bottom, we can see that the autoencoder was not able to reconstruct the measurements that are coming from the CT and CT1 and CT2. In this part, we consider differential protection. So basically, it was easy for the autoencoder to detect the anomaly with 100% recall and 100% precision. And then the final scenario that we consider was the replay attack. The replay attack was the most difficult one to detect. And the reason behind that was that in the replay attack, we used the real measurement from the same substation. So as you can see, the recall has dropped to 95 or even to high 82%. So that's the most difficult type of attack. to identify using these machine learning-based methods. So we are now working to see how we can improve the performance of machine learning-based anomaly detection system to address this type of attack. And finally, another very important topic that I would like to mention is the adversarial attack or evasive attacks against machine learning-based anomaly detection systems. So after we developed this machine learning-based anomaly detection system for substations, we tried to test whether an attacker which has white box access to the algorithm of this anomaly detection system, whether they can create adversarial attacks or craft evasive sample. It was very surprising that we observed that they can easily craft these type of attacks by using another information from another substation or another system, which is not even similar to the substation that was under attack. So the most important take from this analysis was that it is very important whenever we have machine learning-based intrusion detection system or anomaly detection system to keep the algorithms of those systems confidential. Because if the attackers gain access to the algorithms of these machine learning-based intrusion or anomaly detection systems, they can easily craft evasive attacks that can go through them and bypass them and make successful attacks. So some directions for the future. At the moment, I'm working in cybersecurity analysis of electric vehicle charging stations, cybersecurity analysis of microgrid protection, also cybersecurity of wide area monitoring, protection, and control systems, also cybersecurity analysis of integrated energy systems and co-simulation of multi-energy systems are important directions for future research that I'm working on at the moment. So as we move toward smart grids, obviously there are many areas open for future research. Also, I would like to thank many collaborators that worked and supported me for this work. Basically, Professor Deepak Kondrur, which was the lead on the majority of these works. We had help from Dr. Mark Kessel from Hydro-Quebec Research Institute, Professor Scott Sanner, also Dr. Arani from Toronto Metropolitan University, Dr. Haddadi from EPRI, Dr. Anthony Commune, where he's also now at Hydro-Quebec, and Yumen Kha. So I would like to thank them for all their contributions and help with this work that I presented today. So thank you so much for your attention. I would be more than happy to answer any questions. And obviously you have my email address here as well. If you have any questions that would like to reach out, please. I would love to hear more and would like to connect.
Thank you so much, Dr. Abir. It's a fascinating talk, and nice to hear that you're doing all this work, which very key and emerging topic that we're also working on. So I think thank you for your presentation. So we'll open up for Q&A, so folks can put their questions on the chat, and then we can discuss. Okay, so we have some question here from Dave Loper. How have you published the code used to simulate SV and goose signaling? If so, where can I get that? How do you anticipate emerging threat into your systems? Do you collect and label data related to these threats, applying them to local substation models? It's kind of a two-part question. So
wonderful. Thank you so much for the question. So regarding the publication on these topics, if you could please go to my Google Scholar. Most of them are basically published there, but if you couldn't find them, please reach out through my email. I would love to share the publications. So all of them are publicly available in IEEE Explore, so you can easily find the publications. Regarding the second question, as I mentioned, the majority of work we focused on new type of attacks or the attacks that we generated ourselves. And because we didn't focus on misuse-based, for example, anomaly detection system, we didn't use the signatures that exist in the domain. So basically, they were the data that we generated using the co-simulation platform, and then we tried to implement different type of false data injection attacks. So hopefully that answers the question.
I have a question. So these results primarily are using in a simulation environment using RTDS, right? And the
Uh,
substation work, there are two substations, and then this attack models that you have developed, right? And typically, when we look at the denial of service or distributed denial of service, what is the network size? We're looking at some larger network size to really to see whether we can catch the stealthiness of these attack vectors. So have you considered that into your modeling?
Wonderful. Very good question. So yes, we in OpalRT, we first of all we used OpalRT, and in OpalRT you can implement different sizes of the system. So for example, here the test system that I showed was D6 benchmark test system, and we have four generating units connected to the rest of grid through two transmission lines. But we also implemented different tests using IEEE 24 bus test system. We can use IEEE 118 test system. So these test systems can be as large as we like, and then we can implement different type of attacks. So depending on the application that we want to study, here we mainly focus on substation and protective relays. So there was no need to go for a larger test system. So having two substations was more than enough to basically test everything that we wanted. But for different applications, we can consider different things. So, for example, to give you another example, we also studied the attacks for false stripping of circuit breakers through telecontrol coming from control centers. In that case, because we had to deal with many substations, we had to consider much larger test system and then testing if someone suddenly sends a lot of control commands, falsified control commands to several substations, how we can address that. And this was very similar to the Ukrainian attack that happened at many substations attacked at the same time. So yes, depending on the application, it is easy to extend it and use larger test systems.
Thank you. And you mentioned about this adversarial attacks as a future research, in terms of evasiveness, are you working on, some type of model poisoning or data poisoning attacks in this you mentioned you try replay attacks is a hard one, and so I'm just curious to see, how did you, are you considered any kind of scenarios that is actually, talks about evasive attacks, other than replay attacks?
Excellent question. So we didn't work on poisoning attacks. So obviously that's a very important direction for future research to see if some poisoning attack happens during the training of this machine learning based anomaly detection system, what would happen? What we did was that we trained this anomaly detection system, and afterwards we assumed that the attacker has white box access to the algorithm and they want to, but they don't have any information or measurements from the substation. So they have to craft a measurement that can pass through the anomaly detection system first. And second, they have to trigger the actuator as well. So the thing that was making this difficult was that not only the measurement, the fake measurement or crafted seed has to pass through the anomaly detection system, it has to also trigger the actuator to give the result that the attacker wants to achieve. But we observed that it was not as difficult as we expected. So basically, if you have access to the white box model of the algorithm, it is and you have access, for example, to another substation or another test system that's power system measurements, you can generate these type of crafted evasive attacks and pass through the anomaly detection system and force actuators to misoperate.
Thank you. We have another question coming up, I think, how can attackers carry out let me see, attacks in substations or modify or alter the settings of relay and circuit breakers? As generally some kind of security mechanism are deployed already, what is your thought on how does this altering of relays and CBs can occur?
Wonderful question. So there are many different ways that they can do it. It can be supply chain. The most important thing that's happening, and it's very scary thing that can happen, is the supply chain attack. So if during the manufacturing of these IEDs or protective relays, they can just use the loopholes and put something that can be exploited in future. Another way is because we are using more and more industrial Internet of Things devices within the substation. If there are remote connections to these things, they can go and get access to other communication networks or put a malware or something on one of these devices and then exploit it in future. So there are various ways that they can get access to the devices that we have within the substation and then try to implement these type of attacks.
We have one more question from Derek. In your LSTM autoencoder model, how did you determine the reconstruction error threshold for classifying anomalies? And how sensitive is the model to that choice? And what will be your suggestion of choosing a threshold for better generalization?
That's an excellent question. So again, depending on the substation, so it is basically something that depending on the application, it would be completely different. So depending on the training data and the test and verification stages that we have for this anomaly detection, machine learning based anomaly detection system, we have to decide about the threshold that we are using to identify these. So it is not one rule fits all, basically, for all different substation or different applications that we have.
We have one more. How you are communicating the information between the softwares? I'm assuming because the control plane, data plane that you talked about, maybe he's referring to that. It's a very general question, how does the information exchange happens between these different panes, control
So
panes?
wonderful. So it depends if the question is about the test bed that we had and the way that we implemented, or in reality. So in reality, it would be completely different from what we have done in the benchmark test system. So as I mentioned, we use different softwares, Postman and Open Daylight, to implement each parts of the software-defined networking. But if you want to implement these type of things, you can even buy the switches, the real SDN switches, and then you can have physical hardware to implement software-defined networking and test this. But this was obviously in the simulation environment, and we implemented all these things in Riverbed Modeler.
I have one question. We talked about OT SDN and IT SDN. What is the SDN that you are using in the work? And you mentioned something that some of the trip or signals is not transferred from OT SDN. I couldn't understood that part. Maybe,
Right.
yeah.
Excellent question. So I can go back. So basically, if we go to software-defined networking, as we can see, we have these three layers. In the OTSDN, we do not respond to new traffic that comes to the switches. So in each of these switches that we have in the data plane, we have flow rules that are implemented. So as we can see here, the Ethernet source, the Ethernet destination, and packet type all defined. So if you have, for example, 10 different type of packets going through this switch to different locations, the source address, destination address, and packet type all are defined. If we have ITSDN, if a new packet with a new source address or with a new destination address or packet type come to any of these switches, it will be immediately reported to the control plane. Then control plane send it to the application layer, or itself decides how to reprogram the logic in the flow table to send it to the next switch that we have in the system. So if many packets at the same time, many unknown packets comes to the switch, all of them should be reported to the control plane so the DDoS attack can be implemented against ITSDN. But if we have the OTSDN, after you define the logic and you define the source, destination, and packet type, they are locked. So we are not allowing any reporting to the control plane. So if a new packet comes to the switch, it will be immediately dropped. If they want to change it, the engineer has to go to the substation and they have to allow, so there are many different permissions that can be allocated there. So before they can change the flow tables, they have to go through these permissions and then change the logic and again the flow table. And after you set the flow table, again, it will be disconnected from the control plane and it will stay there and no one can change it. So in OTSDN, it would be very difficult to change the flow tables. And if a new packet comes, it will immediately be dropped. So no attack can be implemented.
Thank you. We have one more last question and then we can stop. Is there any difference in the impact of outage of nodes in cyber layer propagating to physical layer in your work?
Wonderful question again. So yes, of course. So if something happens in the cyber layer, it will propagate to the physical layer as well. So for example, as I mentioned, in the communication assisted protection that we have, the two substations has to communicate through the switches that we have, for example, in this figure. So if the switches that we have in the cyber layer, any of them completely fails, so again, the result will be the outage in the physical layer. So for example, the generators will trip, which are in the physical layer. So any impact on the cyber layer will be propagated definitely to the physical layer, and we will see the impact on the physical layer.
Thank you, Dr. Amir. I think, we have one last question. What are the communication protocols that were used to orchestrate the defense when the attacks were identified?
Wonderful. So probably the question is about the anomaly detection system that we have here, CDS. Here we assume that the cyber attack detection system sends a goose message to the IED to block the measurements that are coming that are malicious. So if the question is about the cyber attack detection system, here we use the goose messages to block. And they were authenticated, so no one can attack that. That's a very good question because that also can become a source of attack. But here we assume that the goose messages here are authenticated, so no one can attack it.
Great. Thank you. I think, we have a lot of synergies at UND. We are developing a test bed with Edge AI, collections of NVIDIA devices. We have modeled, as part of a DOE project, we have done a lot of work in different types of attacks and also deployed a lot of machine learning approaches. I see some similarities what you have done in this setting. Maybe we can connect to your test bed and either remotely, and find ways to work together. I think,
Wonderful, of course.
and
Of course.
one other thing before we depart, I think I would like to bring up your help and see whether if you can also help in promoting our IEEE Cyber Conference that
Of
you're doing
course.
in October. And this is the fifth year we're doing. Maybe you could encourage this with your faculty and students and maybe submit some papers. And it's also virtual, and I mean it's also on campus and virtual. But I think there is a call for a special session on power grid security. So I would love to have something from you, and if you can help and promote or
Of
in
course, of
UK.
course. It would be my pleasure.
And we
Definitely.
can,
Yeah.
we can add you to our TPC and help us promote the conference. That would be awesome. And are you coming to the general meeting next week?
Unfortunately, not this year. No.
Okay. Okay, sounds good. Thank you, Dr. Amir. I think it's great to have you here. I think I look forward to chat with you and maybe find ways to collaborate.
Wonderful. Of course. Thank you so much again for having me. It was a great pleasure attending this webinar.
Thank you.
Thank you so much. Bye for now.